All right, we are set. So once again, a very good evening to everyone. Welcome back to our lecture sessions of the Further Calculus for Engineers MAT 455. All right, so tonight lecture class is actually to replace last Thursday that I cancel due to some personal working reasons. So tonight I don't wish to spend too much time. Basically, I just wish to complete everything in 1.5 hours. So without further ado, we will continue with the lecture 23 of the surface integral. We actually have started this lecture 23 yesterday by introducing to you how actually surface integral or the flux can be computed on the three-dimensional vector. In doing so, we need to first convert three variable functions into two variable function, and next to compute the corresponding normal vector n. And by having that, then we can plug in everything to compute this flux, double integral vector f dot of the normal vector n with respect to the surface. Again, since surface consider two-dimensional plane, it's either you use the rectangular plane or you use the polar coordinate plane. Now, remember yesterday I also mentioned I have highlighted one thing inside the definition that your vector f should be continuous partial derivative for the first, all right, in order for you to apply the surface integral. Okay, as I mentioned yesterday, I just want you to take note of this highlighted part, but you don't have to worry anything because no computations will be involved. Okay, basically it serves as a purpose in the later lecture 24 when we move into it. All right, in terms of finding the surface integral, the most important or the critical calculations is only a pair. If you have something pointing upwards, yes, this is the first surface, first flux that you need to compute. Then the second flux will be the corresponding acting downward. Again, you just need to compute a pair of opposite direction of each other, the flux, then you can just add them up for the resultant, the net flux computation. Whatever at the horizontal or orthogonal, it's not of our concern. It will always be zero. And also, we learned a bit about how to parameterize the vector from three variables to two variables, and how to compute the unit vector for upward and downward. All right, so we actually yesterday stopped at this example number 2 for the first surface calculation. And I also asked you to at least try on your own to get the second surface and see whether you can familiar yourself with the computation. All right, so for the second surface computation, okay, I will go through slightly quickly. If you can't catch it, then you let me know. All right, yesterday we have computed the second surface equation with respect to x equals to 0. We have also computed the normal vector n acting downward, -1, 0, 0. Hence, by the second surface computation flux, S2, which means we can now compute the double integral of the vector f dot the normal vector n with respect to the surface. Now, I also did reminded and mentioned to you yesterday, whatever double integral that you have used in setting up S1, the exact same setting can be used for S2 because we are just referring to the same surface, just in different opposite direction. So here, 0 to 2 pi, 0 to 2, r dr d theta. So I will use the exact same setting. That is, integrate from 0 to 2 pi, integrate from 0 to 2, and then the integral still r dr d theta. The only part that will be different is the inner computation. Well, the vector f would still be the same. That is x, y, z here. Therefore, I will just copy it. Oops. Okay, but the n computation for the normal vector acting downward, it's actually -1, 0, 0. So this is the one that I will use here. -1, 0, and 0. Now, by the dot product, you simply just need to multiply component to component, which I have demonstrated a few times previously. X multiplied with -1 plus y multiplied with 0 plus z multiplied to 0. All right, and then r dr d theta. So in the end, you have the function that left only with the variable x, -x, r dr d theta. And remember, in this question, surface number 1 and surface number 2, we actually parameterize the variable of x such that for second surface, x equals to 0. Again, x equals to 0. Therefore, if you substitute the x here with 0, eventually you notice that the whole computation here is the double integration of 0 dr d theta. And remember, under the finite integral, with 0, the answer will always be 0, which means the flux acting downward has the value of 0. And finally, we say that the total net surface integral, that is double integral for S, f dot normal vector n ds, is simply the first surface plus the second surface. The first surface we compute 24 pi. The second surface 0, therefore the net will be 24 pi. Now again, I just want to remind you, second surface acting downward, not necessarily answer must be 0. I just want to warn you for one more time. For S2, the surface acting downward, not every time you will get 0. It's just so happen in example 1 and example 2, you got the value 0. Sometimes there will be value for the surface acting downward. And for that, we will see in the next example 3. All right, so whatever we cover so far in example 1 and example 2 are all in polar coordinate. Again, because in the equations given, we can always find a pair of squared variable, add them together. This is a circle equation. Just like in example 1, we also have x squared plus y squared, a circle equation. So whenever we detect that is a circle equation, we apply polar coordinate. All right, so this example 3, we will see how we can actually apply the Cartesian rectangular coordinate dx dy or dy dx in finding the flux. Now the question, a vector field F equals to 2i plus j plus 3k exists over a surface S defined by 2x plus y plus 2z equals to 4 and bounded by the side surfaces in the first octant. Your target now is to evaluate the flux over the surface indicated. Now look carefully from the graph given. You notice that the surface, there is one surface being highlighted or shaded. If you look carefully, this is the triangle surface being shaded here. Therefore, you are actually evaluating the flux acting on this plane. So this is the one different from example 1 and 2. Look carefully. If there is any diagram or figure given, you please take note carefully. Is there any shaded region given? If there is, then you must evaluate the flux based on the shaded region given. All right. Okay. Just to also let you know, different shaded region gives you different surface integral. That's why you must be very careful on it. Now, also, you notice that the word mentioned first octane. So I hope all this highlighted part gives you some information. If this is the shaded region and you notice that they are actually on XY plane, again, this shaded region, this little triangle is actually lies on the XY plane. You should know that under XY plane, the equation will be Z equals to 0. All right. First octane actually means that X must be 0 or positive. Y also must be 0 positive. Z must also be 0 or positive. So these are some of the keywords you should pay attention and remind yourself again in this vector calculus. Now, we denoted that this little shaded region triangle is located or lies on the XY plane. It has the equation Z equals to 0. Therefore, the flux acting in opposite of Z equals to 0 must be another equation derived from here. So here we have 2x plus y plus 2z equals to 4. Z equals to 0 is the first Z equation. Therefore, the second Z equation should be obtained from here. So 4 minus 2x minus y. Okay, remember, you always obtain a same pair of the variable function in surface integral. Therefore, Z equals to 2 minus x minus 1 over 2y. So now this is the first surface acting upward. Z equals to 0 is the surface acting downward. Okay, upward or outside are the same. Okay, because when you look at the z-axis on top of the diagram, you find this triangle shape there. Okay, the projection of the surface. Okay, any questions you can ask. So here, this plane, when viewing upward, has this triangle plane. Therefore, this is S1. Z equals to 2 minus x minus half y. The second surface will be the xy plane, the shaded region here, Z equals to 0. Now, this is what I mean by parametrization. When you have parameterized the variable Z, now in your mind, this Z becomes the function f. Okay, just like how we did previously in yesterday class. Whenever you change the variable Z, now Z should be disappeared. You replace it with the function f so that later when you compute the normal vector n upward, you should know that this must be negative differentiate f with respect to x, negative differentiate f with respect to y, and z must be positive 1. Whichever variable that you parameterize, the normal vector is always set to 1 automatically. Same goes to here. The normal vector n, because S2 is acting downward, this gives you positive differentiate f with respect to x, differentiate f with respect to y. This is negative 1. Okay, opposite sign. So by right, the calculations of this normal vector, okay, if you compute, differentiate negatively, x for here gives you positive 1. All right, differentiate negative x, you get negative 1, but negative of negative 1 gives you positive. Here, negative differentiate f with respect to y, you get positive 1 over 2. And this is 1. So for the second, normal vector should be easy because f is 0. Differentiate anything with respect to x or y should be straightforward. All right, just to remind you, the first surface that we find is always acting upward. The second surface that we find is always acting downward. So now, let us proceed to find out the surface integral for the plane S1. The double integral of the formula f dot normal vector n for the surface S. Now, look carefully. In this question now, there is no any circle equations found because all the variables are just 2x, y, and 2z. They are just a straight line plan. Even in the diagram also given is a straight line plan. But you notice that the shaded region is a triangle. Again, the shaded region is a triangle. Look carefully. X has the value 2, y has the value 4. Okay, so this is the origin 0. Okay, therefore, we will be using rectangular triangle or rectangular coordinate, sorry, to plot it. So just let me indicate again. This is the triangle that we have. For the x-axis, we have the value 2. For the y-axis, we have the value 4. All right, so double integral. F has the vector here, 2, 1, and 3. 2 component m, 1 component n, 3 component p. So 2, 1, 3, just a constant number here. Dot, oops, sorry, not here yet. Okay, close the vector, and then dot the upward normal vector, 1, half 1. All right, so let me remain ds first. So if I try to compute the inner part of the dot product, it will be 2 multiply 1 gives you 2, plus 1 multiply half gives you half, plus 3 multiply 1 gives you 3. Now, once you set up this integral, it's time to decide. This is a rectangular coordinate. You can choose either dy dx or dx dy. All right, so either you want to choose x or choose y. Remember, the plane equation is 2x plus y plus 2z equals to 4. All right, the plane equation again, 2x plus y plus 2z equals to 4. We also have the second surface z equals to 0. Remember yesterday, if we have the same pair of equation in variable z, we can solve them simultaneously. All right, so 2x plus y plus 2z equals to 4. We have z equals to 0. Therefore, combining everything together, we have the equation 2x plus y equals to 4 because z is substituted by 0. Now, this is a straight line equation. Depend on which one you want. If I choose y equals to 4 minus 2x, again, this is the straight line equation of this actually. When you substitute z equals to 0 into here. Now, if I rearrange, I have y equals to 4 minus 2x, which means I can consider using dy dx in my integral. Okay, remember, dy dx is the movement of the graph from the lower part moving upward until you touches the line. This is horizontal line having y equals to 0, moving up until you touches y equals to 4 minus 2x. All right, this movement from lower graph to upper graph is happening in between x0 and x2. So the outer interval 0 to 2. Now, if you still ask me, sir, why this is the region, look carefully in the question. We already provided you the shaded region, the little triangle here. All right, this is the little triangle. Therefore, this is the whole region shaded. And now you are going to form the double integral based on this shaded region. All right, so like I said, in double integral, it's up to you. You want to use dx dy or dy dx, depending your convenience of moving the point. So to me, here, moving y down to up looks easier because I already have the good equation y equals to 4 minus 2x. So simply proceed to evaluate. 2 plus half plus 3 actually gives you a constant number. Okay, again, y equals to 0 to y equals to 4 minus 2x. Here gives you 11 over 2 dy dx. Well, just a constant number. Constant, you can actually pull out if you want. Okay, letakkan constant di luar. Now you can integrate with respect to y. So you obtain the y variable from 4 minus 2x to 0 with respect to x. All right, constant can be pulled out. So now substitute this upper and lower limit into it. In the end, I have the next equation 4 minus 2x to be integrated with respect to x. Again, this is also a very simple integration, which gives you 11 over 2, the constant multiplier. Next, integrate 4, you get 4x, minus integrate 2x, you get 2x squared over 2. This is evaluated from 2 to 0. Okay. Now, the integration part, the evaluation here should be straightforward. In the end, you get 11 over 2 multiply 4 multiply 2, 8 minus 2 squared, 4, which gives you 4. In the end, the flux acting upward is 22, the value. Okay, the flux acting upward is 22, positive. So again, this question example 3 is just to let you know, besides the polar coordinate, we also have this rectangular coordinate dx dy dy dx. So make sure you are still familiar with the order of the integration, depending you want to move the graph from left to right or lower to upper graph. Okay, to get the equation, solve the first surface and the second surface simultaneously. Now, we have done with the upward flux, so it's time to look into the downward flux. Again, for the downward flux, the setting is identical. Like I said, how you set up the double integral in S1, you can use the exact same double integral for S2. Just make your life easier. So now I'm going to set up first whatever I have done in the previous. So S2, the second flux is again double integral of f dot d normal vector n with respect to the surface. So just now I use x0 to 2 double integral y equals to 0 to y equals to 4 minus 2x. Even the vector f will also be the same, 2, 1, 3. So I can just fill in the blank quickly. 2, 1, 3. Dot. The only thing will be different is the normal vector. The normal vector acting downward, if I refer back to the slide, will be 0, 0, -1. So dot 0, 0, -1. And the rest will be the same. This is still dy dx. So if you look carefully for the whole setup here, the only part that is different is the end. The rest here, that in dark blue color, are exactly the same as in S1. That's why I mentioned yesterday, once you know how to compute S1, S2 should be easier to handle. As usual, expand the dot product. So from 0 to 2, so here from y equals to 0 to y equals to 4 minus 2x. So 2 multiply 0, 0, plus 1 multiply 0, also 0, minus, okay, because 3 multiply -1 is -3. So plus -3, which means minus dy dx. Okay, there is a negative value here, okay, because 3 minus -1. So this is a negative value. Well, as usual, if you have a negative constant, you can pull it out. So once you pull out the constant, if you integrate with respect to y, you will obtain the variable y. So this part, I believe I do not have to mention any more further because this is just the usual integration that you have handled and dealt with many times before. So again, this gives you 0 to 2, substitute upper, 4 minus 2x. Even if you look carefully, the integration here is exactly the same like in the first S1. Right? So this gives you -3, integrate 4, 4x. Integrate 2x, 2x squared over 2. Substitute upper limit 2, lower limit 0. So you get -3 multiplied by 4. This gives you -12. Now, this is what I mean just now. Sometimes the flux acting downward has value. Okay? Not always you will get 0. Not always the case. That's why you have to really compute everything carefully. And also, as I promised yesterday, whatever flux acting downward, the value that you obtain is always negative because opposite of the direction. So -12. In other words, if now I want to conclude all my surface integral flux computation, f dot n of ds, this is just S1 plus S2. S1 just now we have the value positive 22 plus S2 we have -12. So in other words, the net flux or net surface integral this time is given by the value positive 10 only. So this is the demonstration that I want you to take note because sometimes the flux acting downward has some negative values in which in the end, when you conclude S1 plus S2, the value net resultant surface will be different. All right. So again, for example number 3, look at the diagram given. The diagram actually gives you the shaded region on the XY plane. That's why you have to be careful when finding the surface integral. All right. Now, for the example 4, I will not go through with you example 4. Instead, I will just give you some hint you can later try on your own. Now, in this example 4, calculate the surface integral of the vector f longer function over the surface of the plane x plus y plus z equals to 1, bounded by the side surfaces. All right, bounded by the side surfaces is actually the same meaning as first octant. Okay, just in case if you are not aware, side surfaces has the similar meaning as first octant, which means x must be bigger or equals to 0, y must be bigger or equals to 0, z also must be bigger or equals to 0. Now, if you look carefully, the way the question is asked is just the same like in example 3. The only difference is that in example 4, I do not provide you any graph. Okay, I do not provide you any graph. In other words, you want to use x, y, or z in your parametrization, also possible. If you don't catch my meaning, again, let me flip back to example 3. Example 3 says that I have a shaded region here. This shaded region is xy plane, z equals to 0. That's why I have to make sure my S1 also following variable z, just to match with the xy plane. Now, in this example 4, I do not give you any shaded region or graph at all, which means you are free to pick either you want x equals to 0 and change x here, y equals to 0 or change y here, z equals to 0 or change z here, are all totally up to you. Okay, you can try on your own later. If you switch different variables, what will happen to your final result? So for this example 4, I leave it to you, okay, on your own practice. Right? But I want to go through the last example 5 in this lecture. Again, the region is given. The graph is also given. Now, again, simple question. Find the flux of the vector field F just equal to zk through the surface S, where S is the first octant. Again, the keyword here, first octant, portion of the paraboloid that is cut off by the plane z equals to 4 and bounded by x0 and y0. Now be careful, the graph is given, okay, the graph of the region is given. You notice that now the surface pointing upward is the equation z equals to 4. Okay, this is the surface that pointing upward. If this is the surface z equals to 4 pointing upward, then this parabola here, z equals to x squared plus y squared, will be pointing downward. Now the equation dramatically change here. All right. So just let me write it out so that you know what I try to say here. Because based on the graph given, S1 is always the surface pointing up. In this case, z equals to 4. This is the surface moving up, and therefore this paraboloid curvy shape will be the one pointing down. This gives you S2, also the same equation, z equals to x squared plus y squared. All right, so in this case, we do not need to change any variable because both are already in z, just nice. So z turns to f now. F equals to 4. Here, f equals to x squared plus y squared. Parametrization, changing z into f, so that next, when you compute the normal vector, you should know that pointing upward is negative del f over del x, negative del f over del y, and positive 1. Okay, it's very straightforward. This is a constant number. Therefore, differentiate constant number, you always get 0, 0, and 1. So be careful. This time, the upward normal vector is 0, 0, 1. For the downward normal vector, we flip the sign, it becomes positive del f over del x, positive del f over del y, but negative 1. So this gives you differentiate f with respect to x, you get 2x. Differentiate f with respect to y, you get 2y and negative 1. All right, obviously, like I said, you notice that there's x squared plus y squared. You certainly need to use the polar coordinate. All right, again, like I mentioned, once you found the pair of squared plus, which means this must be a circle, you need polar coordinate. Well, just solve the simultaneous equation. Z equals to 4. Z equals to x squared plus y squared. So now I have x squared plus y squared equals to 4. This is a circle. Simply your radius r is 2. This should be convincing. Now, what about theta? If you remember in example 1 and example 2 yesterday, when I mentioned if the question never gives you additional condition for the circle, we assume theta is rotate fully 0 to 2 pi. Okay, what I did not mention further is that how do I know whether conditions is given or not? Now here is a very good example. X squared plus y squared, you know that this is circle. Again, x squared plus y squared, you know this is a circle. This circle is formed using variable x and variable y. This circle is formed using variable x and variable y. And now you notice that at the very last statement of the question, bounded by x0 and bounded by y0, which means now I insert additional condition for x and y. Because x and y used to form circle, if you insert additional condition to x and y, your theta will change. Right? Your theta will change. Even if you look at the diagram here yourself, you immediately can already see the region R here surface is the rotation from x-axis 0 up to y-axis here pi over 2. This is the half quarter circle, okay, when you view from z-axis. So immediately from here, you already notice, yes, theta is only rotate in between 0 and pi over 2. No longer full rotation. Okay, this is x equals to 0 axis. This is y equals to 0 axis. All right, so this is what I mean by the additional condition. X and y forms the circle. If you give another additional equation to x and y, which means these are these spatial conditions that you need to consider when setting up polar coordinate. Now, we have all the informations that we need. It's time to compute the surface S1 and S2. So first, surface S1 is given by double integral. Okay, always try to write out the formula so that you can take care of what you substitute. Okay, this is the integration from 0 to pi over 2. Because I already know I need polar coordinate, this is the integral from 0 to 2 radius. Now f is also a problem. Please be careful. If your f has only one direction k, it means I, j are 0. Students, we are now talking three-dimensional vector. Make sure you understand all I, j, k should have some values or some variables. If you can't see any, which means they are 0. So vector F is actually 0, 0, and Z. All right. In other words, F is just like 0i plus 0j plus z of k. So the constant coefficient are 0, 0, z here. They are just identical. Right, continue. So here, 0, 0, z dot. The normal vector pointing upward is 0, 0, 1. So here, 0, 0, 1. Like I said, we already know this is a polar coordinate. Therefore, r dr d theta. So simplify whatever is inside the dot product should also be simple. Now you get integral 0 to pi over 2, integral 0 to 2, 0 multiply 0, 0 multiply 0, z multiply 1. You have z r dr d theta. Okay, z multiply 1, r dr d theta. Also, in S1, z value is 4. S1, z equals to 4. Therefore, now you can also replace this total integral is now actually 4r dr d theta. Okay, and the first surface S1, z is actually 4. So proceed to actually find out this double integral. Now it becomes easy. Integrate with respect to r gives you the bracket 4r squared over 2. Evaluated upper limit 2, lower limit 0, d theta. So here, 4 and 2 simplify. And you get integrate 0 to 2 pi over 2. Okay. 2 squared, 4 multiply 2 gives you 8. 8 d theta. All right, and this integration, 8 theta, evaluated from pi over 2 to 0. So the surface integral acting upward should be 8 multiply pi over 2, you get 4 pi. So this is the surface acting upward. Right, should be okay. Next, we are going to look at the downward flux. Remember, second surface z equals to x squared plus y squared. Be careful, the equation is already changed here. But the rest of the setup would be the same. Therefore, I would first copy everything here. Okay, never mind. I can do just below here since I have much space left. So double integral for the second surface, f dot normal vector n ds. Again, I will be having the same integral 0 to pi over 2, same r 0 to 2. F still the same, 0, 0, z. But now I will be dot the product here, 2x, 2y, and negative 1. Eventually, you notice that nothing much is affected because 0 multiplied 2x, you still get 0 in the end. All right, so this integral, if I try to expand and simplify quickly a bit, 0 multiply 0, not affected. 0 multiply 2y, also not affected. Z multiply negative 1, in the end, you get negative z r dr d theta. Now be careful. To replace the z, S2 surface is x squared plus y squared. S2 surface, z is x squared plus y squared. Therefore, when you substitute, remember, now it becomes 0 to pi over 2, integrate 0 to 2, negative x squared plus y squared r dr d theta. Okay, S2, z is x squared plus y squared. But you need not worry too much because we also learned under the circle equation, remember the default equation x squared plus y squared is always r squared. So this part here, you can actually simply replace by this. So negative r power 2 multiply r, you have negative r power 3. So now proceed to find the integral. Negative r power 4 over 4. Substitute from 2 to 0 d theta. Okay, this gives you integrate 0 to pi over 2 negative 4 d theta. Negative 4 d theta, when you integrate, you get negative 4 theta. Substitute pi over 2 to 0. So this gives you the negative 4 multiply pi over 2, which gives you negative 2 pi. And yes, the flux acting downward has the value negative 2 pi. All right, upward 4 pi, downward negative 2 pi. Now you can find out the final resultant flux. What is the net flux of this problem? Okay, let me do at the side corner here. Therefore, the double integral of the surface f dot n ds actually equals to S1 plus S2. So here, 4 pi plus negative 2 pi, you have resultant flux, positive 2 pi. Okay, let me flip the slide back a bit. That's why in the last here, you know that the answer is given by 2 pi, exactly the same. All right. Yes, I also understand. If you notice under this lecture 23, it seems like there is not many exercises provided here. Don't worry. In lecture 25, Stokes theorem, you will go through again all this computation. Yes, in that lecture, there are many exercises that are ready for you to practice on. That's why lecture 23 is just to let you familiar with the parametrization, how to change 3 variables into 2 so that you can evaluate surface integral for 3-dimensional vector. Stokes theorem is really this computation. All right, if you're okay with this, okay, so I will now conclude this lecture 23. Okay, since this lecture is also recorded, later once I upload in the YouTube, you can review as many times as you wish. Hopefully, it can strengthen your understanding better. Okay, now I will close and conclude lecture 23. The time now is 8:55. All right, we will take a 5-minute break. At 9, we will continue with lecture 24, Divergence Theorem. Okay, we will take a 5-minute break for you to get the lecture notes, lecture 24 from the teams. All right, it's 9 o'clock sharp. We can continue the session for another half an hour. So this now brings us into the lecture 24 of the divergence theorem. As I also mentioned a bit earlier, divergence theorem is also very closely related to surface integral. Okay, because some of you may be wondering, sir, surface integral, it's so difficult. You need to compute the surface equation, parameterize it first, and then get the normal vector, and then you compute upper surface plus the lower surface. Is there any alternative? Well, yes, there is. This is through the divergence theorem. Okay, the divergence theorem basically recalls you triple integral. In other words, we will compute the flux immediately in one shot using the triple integral that you learned before in chapter 2. The Cartesian coordinate dx dy dz, the cylindrical coordinate dzr dr d theta, and the spherical coordinate rho square sine phi d rho d phi d theta. Yes, if you do not want to evaluate the surface and the normal vector, then you can choose to evaluate triple integral. This is another alternative. So that's why in lecture 24, there's not much new things covered here. It's basically how you learn to set up the double or triple integral, either surface integral, double integral, or divergence theorem, triple integral. And then we apply the divergence theorem to solve the flux or integral surface problem. That's it. So like I said, the only part that you really need to remind and recall yourself is the three different types of triple integral coordinate system. All right. So this is just some statements. If we have the Q to be a solid region bounded by a closed surface S oriented by a normal unit normal vector indicate outward from Q. Well, this is just theoretically telling you if you have the solid, for example, a paraboloid. So everything pointing outward. All right. It's just a surface solid pointing outward. If vector f is a vector field whose component functions have continuous first partial derivative in Q, now you see this statement again. Oops. You see this statement again, continuous first partial derivative. The one I asked you to pay a little bit attention on it. Then computing surface integral, double integral f dot n ds is just the same as evaluating triple integral divergent f with respect to volume. Remember divergent f, the word divergent here is a dot product. Okay, we actually learned this in lecture 19. Remember the curl, the gradient, and the divergence. So this is actually the divergence, the same concept that you learned before in lecture 19. All right, the divergence theorem gives the relationship between a triple integral over a solid and a surface integral, double integral over the surface of Q. So again, this theorem is just to tell you that just now, whatever we learned in lecture 23 can be evaluated using triple integral. They are the same. All right. So that's why you just need to recall all the three different coordinate systems that you learned before. Cartesian rectangle, cylindrical, and spherical. All right. There's nothing much. That's it. All right. Now, I want to give you the first warning. Okay, again, I just want to give you the first warning. If you still remember, okay, kalau kamu masih ingat dalam Green's theorem, in Green's theorem is to evaluate line integral m dx plus n dy, and we say that evaluating one is the same as you evaluating double integral in greens. Okay, this is the formula of Green's theorem. I hope you remember. And also in Green's theorem, we learned the question may be asked in several ways. Either the question asks you to use Green's theorem to evaluate line integral, or simply asks you to evaluate line integral, or verify Green's theorem. In Green's theorem, when we want to verify, we compute left and right hand side and we make sure they are the same in value. Again, let me emphasize one more time. In Green's theorem, when the question asks you to verify Green's theorem, we evaluate the left hand side and we evaluate the right hand side and we make sure in the end we get the same value. Now, in divergence theorem, this is not always true. Okay, I just want to correct your mind a bit because if you refer to previous version of the lecture notes may also ask you to verify divergence theorem. Let me give you warning. Divergence theorem, it's not always true. If you evaluate left, it must be the same as you evaluate right hand side. All right, it will never always be true because the statement that I highlight here, not every vector f is continuous first partial derivative in the solid Q. That's why I want you to draw attention to this part. The vector, if have continuous partial derivative, then yes, if you evaluate surface integral, and if you evaluate triple integral, you will get the same value. But in real life, not all vector f always continuous. That's why in divergence theorem, left-hand side value and right-hand side value not necessarily must be the same. This is also why in divergence theorem, we will not ask you to verify. Okay, again, in divergence theorem, we will not ask you to verify. Let's say if worst to worst, the question asks you to verify, then the answer must be the same. All right? Again, don't get confused with my words. Later, when you try to do all the practices inside the lecture notes here, you will notice that if you evaluate left-hand side and then right-hand side individually, you may get different values. Don't be surprised. Divergence theorem not always true. However, if the question already stated very clearly, worst to worst, verify divergence, then usually the vector f should be true for both continuous. All right, just to warn you so that you don't feel surprised later when you do your own practice. All right, so this is the only warning, which is why I want you to keep track of this highlighted continuous first partial derivative at the beginning. Okay, remember divergence symbol is F, yeah? It's del dot F. Just in case if you've forgotten what is the meaning of divergence, divergence is actually gradient dot F. Do you still remember what is gradient? Gradient is actually del over del x, del over del y, del over del z. Remember this? If you don't, it's time to do some revision. All right, let's look at the first question. The first question asks you to use divergence theorem to find double integral. If the question asks you to use divergence theorem to find double integral, which means you evaluate triple integral. This instruction is just the same like Green's. If the question asks you to use Green's theorem, you evaluate double integral. So same here. If the question asks you to use divergence theorem, you evaluate triple integral, where S is the surface of the solid bounded by the cylinder, x squared plus y squared equals to 4, z equals to 0, and z equals to 4. N is the outer unit normal vector to the surface S and vector F, x power 3 plus tangent yz I plus y power 3 minus exponent power xz in J plus 3z plus x power 3 in K. Now you will suddenly surprised by how suddenly the vector f given is so complicated and so complex the value. Okay, don't worry. Okay, in terms of evaluation, you just need to know what to do later. All right, the question already mentioned the keyword cylinder. Therefore, in your mind, cylindrical coordinate is what you need. Again, recall the keywords in triple integral. The question mentions cylinder, therefore cylindrical coordinate is what you need. Now I can begin saying that double integral, the flux F dot N for surface with respect to the solid Q here is just the triple integral of divergence. So the divergence of F, I now change the notation del dot F. Okay, remember divergence means del dot F with respect to volume. This is the divergence theorem. In other words, okay, I still remain the integral to be empty first. Divergent del here means in the curly bracket, arrow bracket, del over del x, del over del y, del over del z. And you will dot with the vector, this long string here, component m, x power 3 plus tangent yz, comma, component n, y power 3 minus exponent power xz, comma, component p, 3z plus x power 3. All right, I still remain the cylindrical coordinate to be dv first. I don't want to confuse myself with all the integral setup yet. Just focus on the divergence. Divergence is del dot f. In other words, del over del x multiplied by x power 3 plus tangent y. This means that you will differentiate this component partially with respect to x. Remember partial differentiate? Differentiate this component with respect to x. Now you will notice that actually the structure later will become simpler. Differentiate x power 3, you get 3x squared. Differentiate tangent yz, 0, because no variable x. Next, plus, second, del over del y, dot with this, y power 3 minus z exponent power xz, which means you partial differentiate y power 3 minus exponent power xz with respect to y. Differentiate y power 3, you get 3y squared. Differentiate exponent xz, 0, because again, no variable y. Plus, lastly, the same. So here, let me use maybe black color. Del over del z multiply with 3z plus x power 3. Again, partial differentiation. You differentiate 3z, you get 3. All right. X power 3 becomes 0 because, again, no variable z. Now, up until here, suppose you have gotten what you need. That's why, if you want, you can start to consider building your triple integral. The triple integral that we consider here is cylinder. All right, look at the cylinder. You have x squared plus y squared equals to 4, which means this is the circle on the cylinder. X squared plus y squared equals to 4. This is the circle equation. Yes, cylinder has a circle. Make sure you still remember. So this is the circle x squared plus y squared. If xy forms circle, which means z is the vertical axis that is not changed, and therefore we have r d z d r d theta. All right, z is the vertical line, never change. And you also notice that z is bounded by z equals to 4 and z equals to 0. And therefore, this is the interval that you need. The innermost computation, z equals to 0 to z equals to 4. Next, radius r. Well, x squared plus y squared equals to 4. I hope you really can identify now. R radius is 2. Therefore, r from 0 to 2. Again, cylinder is a full circle solid. Therefore, theta will be from 0 to 2 pi. So all this should not be too difficult for you to identify it. All right. In fact, this is the setup for cylindrical coordinate. You have done it. That's why whatever you learn in chapter 2, make sure you recall and use it in chapter 3. All right. So this is the one that we mean by surface integral, double integral. You convert it into divergence theorem in triple integral cylindrical coordinate. Now, let me copy again this whole line in the next slide, okay, for us to actually go through more clearly. So integrate from 0 to 2 pi, cylinder full circle, from 0 to 2, the radius, integrate from z equals to 0 to z equals to 4, the z equation. I have 3x squared plus 3y squared plus 3, and then r d theta. Okay, just to make sure you understand, r d theta, it's not related to the bracket yet. Oops, something is missing. I forgot my dz. Now, you notice that there are still variable x and y inside the integral. Well, following the polar coordinate transformation, x and y should not be there anymore. Therefore, we need to think how to change it or how to convert it. And in fact, not so difficult, because if you look carefully, 3x squared plus 3y squared, I can rewrite this as 3 factor out in the bracket x squared plus y squared. X squared plus y squared is a circle. Circle can be polar transformed into radius squared. All right. In other words, this part is actually 3r squared. Okay, let me go quickly a bit. 3r squared multiply r, 3r power 3, plus 3 multiply r, 3r. So now dz dr d theta. First, we want to integrate with respect to z. 3r power 3 plus 3r, there's no variable z here, so they just assume like a constant. Oops, again, I always forget the other integral here. From z0 to z4. So 0 to 2 pi, integrate 0 to 2, integrate with respect to z. So 3r power 3 plus 3r. Tak berkaitan, put aside. Now I return variable z here. Evaluate from 4 and 0. All right. So if you substitute 4 into it, you get 4. Now, let me do a little bit of a rearrangement here because I also noticed that 3 and 3 can be factored out. Okay, 3 and 3 can be factored out together with 4. I actually have 12 outside. Okay, kadang-kadang saya akan tulis dengan cara yang lain. Make sure you can see and identify the difference and the similarity there. So now I am leaving r power 3 plus r, dr d theta. Okay, 3 and 4 multiplied. So this gives you, again, another simple integration with respect to r, gives us 12, integral 0 to 2 pi. R power 3 is integrated to r power 4 over 4 plus r squared over 2. Substituting 2 and 0 and then d theta. Okay, 2 substitute into it. 2 power 4 over 4, you get 4 plus 2 squared over 2, you get 2. So 4 plus 2, you actually get 6. So 6, put it out, you have 6 multiplied 12, 72. Okay, kalau tak nampak, tak apa. Let me write one more step just for the sake of making everything clear. Into it, you get 6 and then d theta. So this gives you 72. Integrate with respect to theta, you get theta, and then 2 pi until 0. So this is simply 72 multiplied 2 pi, and therefore you get the flux to be equal to 144 pi. So this is how we use the divergence theorem to find the surface integral. Again, when the question asks you to use divergence theorem, the instruction is to use triple integral. Divergence theorem means triple integral. Green's theorem means double integral. Okay. After this, if you have free time, just simply test yourself. If you do not want to use divergence theorem, instead, you want to evaluate surface, cylinder up and cylinder down surface one by one. See whether you get 144 pi later. Okay, this is just for you to actually convince yourself. If you evaluate the surface integral, the surface of the cylinder facing up and facing down, you will notice that in the end, your final answer will not be 144 pi. Because this vector f is not continuous. Okay, that's why we do not have to go until that extent. But again, let me draw out something important, the important part that you really need to know. Make sure you remember divergence. Divergence is actually partial differentiate, partial derivative with respect to x, y, z variable respectively. That's why in the examples or in the questions that we give you, vector f is always looks so long and complicated. Okay, don't worry. When you partial differentiate it, usually the output will just be a small value. Okay, all right. That's it for tonight. Okay, actually, I just want to introduce to you first about the divergence theorem in relationships to compute the surface integral. Tomorrow night, we will go through more examples about this lecture 24. So tomorrow night, additional class, I just want to focus on divergence theorem because most of the time, divergence theorem is also a final exam popular question. Okay, because divergence theorem tests triple integral. We can use
Doctor,
one, yes,
the next slide, the integration part.
yeah,
Why it became 12 in the front of the integration?
this. You mean this?
Yes.
All right, okay. All right, never mind. Let me explain a bit. So actually, this 12 is actually taken from here. Okay, integrate. Okay, here I actually extract 3 out first from here. And then z, if you substitute 4 into it, you get 4 minus 0. That's why 3 multiply 4 gives you 12. I factor it out.
I see. Understand.
All right, great. Okay. So to the rest also, please let me know because sometimes I will jump some certain steps which I may find it easy. If you lost, just let me know and I will explain it further. Okay, all right. So again, because under divergence theorem, we can actually test you many things in one question. Divergence theorem immediately can ask about the double integral surface. Can also ask you triple integral in chapter 2 using different coordinate system. Okay, so that's why divergence theorem, this question is quite popular and what do you call it, frequent in the final exam. That's why I plan to do additional class tomorrow night just to go through more questions as possible for you to understand better. All right, so that's it for tonight. I will stop the recording. And later, I will upload this recording in the YouTube as usual. Once again, thank you for your attendance tonight and see you tomorrow. Thank you and have a great day. Bye-bye.